That's good. And we're good.
All right. Sounds like we're landing something on Mars. Okay, welcome everybody. So in our, I got some good feedback from Tuesday. Just informally, I'm going to ask you with a survey at the end of this about exactly what people like. I think people like the ability to ask questions on Tuesday. Some people said time boxing it would help, just so that it's not, again, going into the imbalance in time. So I'm going to try to present a little bit today, kind of bring home one idea that I like from the lecture that we can get you to think about it, hopefully in just a different way. And you can fire your questions at me again, and we'll just see how it goes. And I'll ask you for your feedback. So the goal for lecture 4 was I went through, these topics. We had started off on Tuesday talking about the fully discrete graph search version of dynamic programming. And then we worked our way from the purely discrete, where it's pretty simple to think about, at least in my head, to think about, and then transitioned over into the continuous. And we did it in parts from continuous states, and then continuous actions, and then continuous time. In continuous time, we got this sort of beautiful equation, which is the Hamilton-Jacobi-Bellman sufficiency theorem, which says roughly that if your gradients match this condition that we wrote down on the board, then that's a sufficient theorem for optimality. Okay. Now I do want to make sure that that the thing I wrote on the board was sort of the informal derivation, and there are a few technical conditions required to make that true. The obvious one is that it depends on the derivative of the cost to go function being defined everywhere. But there's a few other technical conditions that are written carefully in the notes. But that's I think in the whole presentation, I'm trying to light up your intuition for these things. And then we talked about, I introduced the linear quadratic regulator, which some of you will have seen before in applications. If you've ever played with quad rotors, you've probably used a linear quadratic regulator. It's a staple of control, of modern control. It's actually also come back into popularity in the last year or two, because the reinforcement learning communities used that as a problem where they can start proving theorems about what reinforcement learning does for the linear quadratic regulator. First just in the policy gradient regime, and then in the sort of finite data regime. And this has become, again, a workhorse where we can actually understand what's going on. And even in the next lecture, next week, you'll see, I'll try to make the point that it's pretty relevant, even if the systems are nonlinear. So I wanted to dig into this dichotomy between discrete and continuous time. There's a lot of things to know about it. And so I thought I'd work through it sort of on the whiteboard in a second here in a slightly different way to make sure you're thinking about it in a couple different ways. And hopefully that'll just help build up the whole intuition. So this is the, that whiteboarding app. Now, hopefully you won't be writing on it quite as much. This one's meant to be me writing on it. Okay, so I want to compare the linear quadratic regulator. I wrote it on the board in continuous time. That's sort of my favorite version of it. But there's also a discrete time version of it. So again, we can sort of look across the discrete time, continuous time divide and see if we understand what's going on. Okay, so in continuous time, we'll do it this way, and then discrete time over here, make sure it's showing up in the right. Okay. So even, my favorite place where all the algebra goes through and sort of something that's good for board work is just to think about the double integrator. So where it's the simplest linear system. Okay, so I've got Q double dot equals U, it's a second order system. Okay, so in that second order system, I think of having the state Q and Q dot, right? And then I think about having the dynamics which is q dot, and then u, which if I want to write that as ax plus bu, I can do that by choosing a equals 0, 1, 0, 0. Not a very interesting a, but it's still an a. And 0, 1, okay? And then the simplest LQR problem I could write would be to say I want to minimize some long-term cost where I've got x transpose qx plus u transpose ru. And I'll just choose Q equals the identity matrix. It's going to be 2 by 2. And R is the just 1, actually. It's the 1 by 1 identity matrix, so it's just the number 1. Is that whiteboarding thing working okay for people? Yeah, good.
I think you're writing off the bottom.
I think you can scroll. So yeah, this one has the ability to, oh, look at that. Now I can see everybody's mouse. Yeah, so if you click on the hand and you can just, or sorry, you don't have to click on the hand. You should just even use the arrow keys to go up and down, or, oh, interesting. So I have to scroll. That's lousy, but I will try to scroll too in case anybody's watching on over that. Okay. Yeah, I can drop the link here again. Okay, thanks, Dr. So this was the example I used in the lecture last time, and the solution to this is actually that I get the cost to go function, where s, it works out to this, have this nice form. It's square root of 3, 1, 1, square root of 3. Okay, so let's just think about what the discrete time version of this looks like. So in discrete time, I'm going to have a function that looks more like axn plus bun. Is that on the screen or not so much? Is that showing up for people or not? Oh, I see it's up here. Yep, my bad. Okay, good. And my cost function is now going to take the form sum over n x transpose n qxn.
Where did s come from again?
I'm gonna make that connection. So what is x going to be in the continuous, or in the discrete time? I'm going to call it q for, I'm going to q at time n. Maybe I won't call it q dot. That's a dot sounds too much like the derivative. I'll just v for velocity here. Okay. And then my xn plus 1, the simplest approximation of the discrete time, of the continuous time into the discrete, would be to do some sort of Euler integration. So if I say h is my time step, then I can say this is qn plus h vn. And this one is vn plus h un. Which again, I can write as a, now it looks like 1 h 0 1, and b is 0 h. My q, I'll do almost the same. Maybe just to keep the integral looking the same, I'll multiply it by h. So I'll do h times I 2 by 2, and r will just equal to h. So if I called this original s the continuous time s, then what can I say about the discrete time s? That's the question. Anybody have any guesses of what you could say right off the bat?
Is it H times S?
It's not as simple as H times S. That's an awesome guess. And this is one of the key ideas, I guess, that I want is that there is a fundamental difference, and we're going to see it in these equations. Well, so one thing we'd like to be true, which is true, is that if I take the limit as h goes to 0 from above, then s dt should go to s ct. That is true. But there's something else we're going to find out is true, is that SDT for all h's greater than 0 is strictly greater than SCT. Now, I just wrote an inequality that's kind of, I try to write it with as a matrix inequality. But when I say something like that, what I mean is that it, in the sense of a matrix positive definiteness. So what I mean is that X transpose S dt X is greater than X transpose S ct X for all X, or you could say the S dt minus S ct is positive definite. So why? Okay, so first of all, what does that mean? It means it costs more. The cost to go from starting in some state is more in discrete time than if you're in continuous time for this just straight up approximation. Why does it cost more to be in discrete time?
Because if you were in continuous time, essentially you'd be like continuously decreasing the cost by very finely upgrading the forces that you were applying. Whereas here you have to, over the entire non-zero block H, apply this like chunk of force.
So good. That's exactly right. So if you think about the discrete time is basically adding a constraint. There's a new constraint you didn't have in continuous time, which is that you must have, even if you perfectly integrate the dynamics over, you can have a discrete time linear system match perfectly. But the new thing that happens in the discrete time here is that you must hold the same value for some discrete interval of time. Okay, so let me say that in another way here. So if I think about one of the great things, okay, so when I run LQR in the original case, I also get a K, right, where the optimal controller in linear systems, everything goes through. So what we could say is that our closed loop dynamics, if I'm running that controller, looks like x dot equals a minus bk times x. Okay, which means x at time t is going to be e to the a minus bk t x0. You don't, this is sort of, it's not an essential thing for the class, but you can integrate that in closed form for the, in the case of a linear system. And so I know that the u I'm going to follow is just also looks like this. So basically the picture you should have in your head here is that if I look at time and I look at the continuous time convergence from some initial condition for a quadratic cost, it's going to be pretty simple, right? So it's going to be some sort of quadratic decay to 0. Okay, this is u as a function of time. If I look in discrete time, then the equivalent, I have to do a little, what I'm going to say is that u of t is like u. If I wanted to somehow draw the thing that I'm actually applying to the robot, then I have to do something to bridge the ct dt divide. So it's something like this, but the picture you should have in your head here is that I have to take steps, right? Or to draw it right on top of the other one. Those should all be the same width if I was a better artist. Okay. But by making a discrete time, I mean, I can integrate a continuous time forward for some fixed interval in closed form. So that's not where the approximation is coming in. But I've written a different optimization problem, which says I only get to change my control action every h seconds. And that changes the class of possible trajectories that I can execute. Okay. And in general, whenever you add a constraint to an optimization problem, the cost goes up. Okay. So let me show this to you numerically. If you come back to the to my screen share on Zoom for a second, I'll just show you that this is true numerically, and it's easy to see, but I think compelling to just see that the numerics match the math. This is a very simple typing in of those equations. I've made my A and B matrices, I've made my Q and R matrices. As advertised, I can just call linear quadratic regulator and get back those K and S. Okay. I'll also just to think about the magnitude of S, I will just plot the eigenvalues also. Okay. So when I run that, which I did, then I get square root of 3, 1, 1, square root of 3. Everything's good. And the eigenvalues come out to that. Yeah, I don't really know what those eigenvalues are yet. But what matters is the relevant size of those eigenvalues when we do the discrete time. So the discrete time is just as simple. I just wrapped in a little sugar so that we can update it on a slider. But so now it's the AB I just wrote on the whiteboard. Okay, Q and R that I just wrote on the whiteboard. And there's a discrete time linear quadratic regulator. These are numerical, algorithms that solve a Riccati equation behind the scenes, but there's good numerical recipes for that, which we've typed in. I'll plot its eigenvalues and eigenvectors. Okay, and remember I started off, at 0.73, 2.73. That was our gold standard. I guess when I zoomed in, make the text big, I can't see them both at the same time. I didn't think of that, but these are bigger numbers. 1.27, is bigger than the 0.73 or whatever, and this is bigger than the 2. That's when h is 1, which is a relatively big time step, which is a silly thing to say since I can put no units on, but okay. If I start making it smaller, then in fact, you could think about the constraint being less and less severe because I'm allowed to make control decisions more often. And in fact, the cost will go smoothly down. Remember, S is the cost to go, so it has that direct interpretation. And in the limit, as h gets to 0, it will go to the numbers above. Yeah. If you actually ask the discrete time to do with h equals 0, it'll complain. So this is stopping at 0.01. But because if you're asking, in that case, the discrete time formulation sort of goes singular. But the limit is correct. Okay, so let me just say that important point again here, which is that if I'm thinking of this on the right as, I guess I don't know how to use a pointer on this particular whiteboard app, but the one on the right here is more constrained than the one on the left. And in general, if I have an optimization problem, min over x of f of x, and I compare that to the same optimization problem subject to some constraints, then always the optimization problem on the left will have a minimum cost that is less than or equal to the one on the right. Okay, adding constraints can make the solution that was optimal on the left no longer viable. Okay, but if it could do nothing, and then the optimal solution stays the same. But the only thing that can happen when I add a constraint is it might be that the solution that used to be optimal was not available anymore. Okay. Cool. So that's just another way to think about discrete versus continuous time, and it really matters. I mean, so people argue that, for instance, in real control systems, you end up you are sending with a digital computer commands at some at some fixed time scale. So actually, the discrete time might be a better representation of your system. But actually, in my world, I tend to prefer the CT because everything's tends to be more beautiful in the CT. And what do I mean by that? So, well, even in the LQR, the equations are simpler in continuous time versus discrete time. But especially when you're thinking about physics, the equations of motion are written in continuous time. You have to be exceedingly careful to not break structures if you make discrete time approximations. So for instance, the conservation of energy, if I have a passive system with no torque being put in and no damping, you'd expect energy to be conserved. That's a nice thing about physics, right? If you take a nice energy conserving continuous time dynamical system and you make a discrete time approximation, that approximation will not conserve energy unless you're exceedingly careful to make sure that it does. And there's ways to do, like, if you've ever heard of symplectic integration, or there's field of trying to do that, which developed originally for sort of cosmological sort of computations where you expect little dissipation to matter, but people use it in robotics now. It's harder. Some of the other, some of the things that we do in the algorithms coming forward that will depend on the structure of the equations, the structure of the physical equations, will break when you try to do it in discrete time. Okay, so I tend to prefer continuous time. Ironically, the reinforcement learning community tends to, just almost historically, I think, has tended to mostly focus on discrete time. You'll see almost no mention of continuous time in reinforcement learning. I think it doesn't matter as much there because you're not trying to exploit the structure of the equations the way I am. And you can Google and find a few canonical papers where people do this continuous time formulations of the RL algorithms, but they tend to not be mainstream. Okay. Right. So I think there really is a really nice, beautiful thing in continuous time most of the time. Okay. Questions about that? Or about anything from the lecture? Let me open it up.
I think this is related to what you were saying about things breaking in continuous time or in discretization. But is it always the case that that format that you wrote for the discrete time approximation, where I'm just taking the floor over continuous chunks, is the optimal discrete time solution? Or like relative to the continuous time case? Or are there cases where like, because I'm discretizing in this way, the discrete time optimal solution is no longer like qualitatively similar to the continuous solution, okay, and like a very different form is necessary?
Yeah, nice. Okay, so lots to potentially say about that, but for when I wrote this floor thing, that was just me trying to so in the discrete time formulation, in my mind, you have set up an optimization problem where you're solving for a finite number of u's over time. And that's all you've ever solved for is those finite numbers. So the only reason, and there's nothing in the optimization problem about the floor. I'm just using that floor in order to draw it in the same way over a continuous interval of time. So that's just me saying, somehow after the fact, you're going to go from those finite set of numbers to something that you're going to send to the robot. And probably the most natural thing to do is just to do the zero order hold. Other interpolations might be possible, but I guess this is the one that's sort of based on the way that I did the numerical discretization is sort of what's happening. But you could try to discretize differently, assuming you had a first order hold or other things. And we'll see some of that in trajectory optimization. The other half of your question, I think, was that do you ever see something qualitatively different in discrete time than you would see in continuous time? Super good question. There are a couple things that are qualitatively different. Maybe the most interesting one right off the bat, even in these linear problems, is you can arrive at a place in finite time in discrete time. You can have solutions that will, so there's a deadbeat solution, they call it, where basically there is a finite control action which arrives at a goal in exactly one time step. In continuous time, that never happens. You would need infinite U, and so instead you converge exponentially. Okay, so LQR will not give you that. It'll still converge exponentially in discrete time, but there are different deadbeat control approaches that will arrive in a single step. So that's just one example, but there are probably other cool examples of discrete time things giving you something different. We'll see also another place, the one place that I do tend to prefer discrete time, and maybe that's a reason RL does also, is it's a little easier to think about stochastic processes in discrete time. You just don't have to think about, continuous time stochastic processes. Everything's sort of just like draw a random number at fixed intervals. And so we do tend to like that. And yeah, I think there are a few things that happen there too that are somehow a little bit different characteristically.
I had a follow-up question.
Yeah.
So I think you may have mentioned this, but if you make like your time interval increasingly small, do you converge to something that in some sense like converge to the same optimal continuous time control?
For any reasonable, that's a good check of the way you've done your time discretization. I think that is typically what you'd want. Yes. You could probably break that, but I think any time discretization that we write down should have that property. That's like a sanity check that you've done a reasonable discrete time approximation. Mm-hmm.
And then if you like solve your system in continuous time, how do you take that solution and actually like run it in discrete time?
It's relatively easy. So if you are going to run this on a digital computer at some rate, what you like is that your rate to be fast enough that somehow the difference between the discrete time and the continuous time doesn't matter. But if I have a function that's defined for all t, then I can certainly sample it at finite intervals. If what I'm actually sending to the robot is a zero order hold of that, a step, then I will have lied to my optimizer and said you have the ability to control torques continuously, but in actuality I'm going to hold them. So it would be better to tell the optimizer that you're going to do that sampling. But in the limit, continuous time for me is like, if you can get close enough to the dynamics of your robot with your sampling period roughly, then you get the benefit of using the cleaner form, which is the continuous time dynamics.
Okay, and I'm probably getting ahead of us, but I'm assuming that your like sensor data is coming in asynchronously in practical applications. Like, what do you do about that?
Yeah, so the honest truth is that I think optimal control doesn't address that commonly. It's typically, there's a unfortunate separation, people tend to do state estimation first and then control, which is something that's perfectly valid in linear quadratic problems, but not for the rest of the problems, but we still do it because it's so convenient. So you end up handling a lot of the multi-rate system kind of things in your state estimation layer, and then having a consistent estimate of state that you send to your controller. So I don't plan to. I'm happy to talk. I'm happy to go there, but that's not a topic that we typically cover, the multi-rate thing. But you're right, it does happen in practice.
Is there a notion of optimization that's like robust to a certain amount of discretization around any given time step? Because like, I suppose what I had in mind for the like breaking example was even just like a really even the pendulum, like trying to swing the pendulum via pushing it like gently up into the balanced position, and just like imagining a case where with sort of like coarse discretization, you're just like kind of like arbitrarily pushing it over back and forth forever. Maybe that's like not the right intuition.
It happens on real robots. I could show you a real robot that's in my physical office that does that. It swings up beautifully, gets to the top, and then goes kind of like this for the rest of time. And it's some combination of the time discretization and backlash and all the little messy stuff that's happening at the origin. So your intuition is right.
And I guess that's why I was saying, like, I wonder to what degree, or maybe we're coming to this, but like, it feels like something that's dissatisfying about this like beautiful idea of like a very gentle, perfect kiss of control is that like, when I think about even just like how I walk around in space, it feels like if everything that I need to do to actuate myself was like so dependent on a kiss of control, I'd be like constantly missing these very unstable equilibria. I don't know, like, I think what I'm trying to say is there a notion of trying to control yourself around equilibria that are like very robust to some amount of noise or discretization errors or whatever, such that and that feels like a kind of a different optimization problem than the one where I'm like very cleanly following these perfect things.
So robust control, I think, is the answer that you ultimately want, and we will get to robust control. It is not. I don't think it's strictly at odds with the kiss of control idea of somehow, like, I think, in fact, for instance, one way that you can hurt yourself robustness is by reading a noisy sensor and making a decision based on it. And actually having less control gains on a noisy sensor can be more robust than having somehow, blowing up some noise that comes in. And for instance, and I think the best thing is to let the physics do all the work, right? The physics isn't, reading noisy sensors or having delays or anything like that. So I actually think it's consistent with the idea of letting the physics do more of the work, and you tend to get robustness. But the machinery we need to talk about that is going to come from, well, we'll see a little bit if you think about robustness to initial condition, we're going to talk about that soon in like a couple lectures. 3 lectures, but robustness to uncertainty, unmodeled errors, time discretization kind of things, that comes in robust control. Right on. So I am gonna try to, so I'm asking for your feedback. So we're still trying to get this right. I'm happy to do anything that gets, more, teaching to work for you. So, but part of that is I said I'd try to respect the time today. So I'm going to slip to Gather Town. I think Eric is at least going to stay here. Yeah, is that the plan? Maybe we could have Dongchan. Do you want to stay here also? And then we'll if there's more people in Gather Town, whatever, we'll go there. And I'm happy to keep answering questions. Yeah. I just want to make sure that people who feel like they want to cut off, they've earned some amount of points, and they're gonna, then this would be a good time for that. But I'm here for the whole time.